Last time we started to talk about the normal curve. And as I recall, we had got as far as deciding that the normal curve was bell-shaped and acknowledged at the same time that there were an infinite number of bell shapes. That is, saying that the normal curve is bell-shaped does not imply a specific curve. Some bell-shaped curves can be more constricted and higher. Some can be more protracted and lower. Let's continue to talk about the normal curve. The reason for discussing the normal curve is that although very few variables, let me rephrase that, although a number of variables and attributes are not distributed normally in the population, this theoretical notion of a bell curve and what we know about it stands at the very center of inferential statistics. Inferential statistics like testing for between group differences, testing the effects of predictor variables on outcome variables and so forth. And we'll get to those inferential statistics later in the semester. As I indicated last time, at the moment we're doing nothing more than taking the parts out of the box and identifying the parts and making sure we've got them. And my comment about the significance of the normal curve, the normal distribution, is not intended for you to try and find some necessary links. I just want you to know that this is a big idea. This whole notion is a big idea because it stands at the heart of much of data analysis. Besides being bell-shaped, which I've tried to reflect here, and I found the deal. It's because I'm left-handed, you've got to go from right to left. It's this left to right thing where I can't see what I've drawn that's messing me up. That's why I was never any good at art. If I'd have worked this out years ago, I might have been an artist. Passing along from that thought. What else do we know about normal distributions, normal curves, other than that they are bell-shaped? Let me be more specific. What do we know about the mean and the mode and the median in a normal distribution? Would you like to amend that? The comment was they tend to be about the same. Would you like to amend that? No? Be more daring. Get to the front of the pack. Be more daring. Feel the wind blowing through your hair. Clean air up here. They tend to be about the same. Would you like to make that statement even stronger?
The mean is in the middle and the most occurring numbers, they're the same. They're the closest number because since the most occurring scores are in the middle of the curve or the bell of the curve, your most occurring scores are going to be in the bell of the curve. Your average score is going to be in the bell, and your middle score, because it is the middle of the bell, is...
Because the bell is symmetrical.
Yeah.
So would you like to rephrase your original statement?
I haven't done that enough yet.
Let's you and me work through this. Let's forget the rest of it. This is my effort at a normal distribution. Scores on the y-axis reflect the frequency with which these xi's occur. Would you agree? So extreme scores at either end of this distribution occur infrequently. As I trace along this curve, tell me when I should stop for the score that occurs most frequently. So you're telling me that the mode is in the center of the distribution. Because this distribution, you told me, was symmetrical, stop me when I reach the median. So would you say that the mode equals the median? This distribution is symmetrical. That is, scores above the center of the distribution are exactly counterbalanced by scores below the center of the distribution. So where would you say the average or mean is in this? Would you say it's right at the center too? So would you say that in a normal distribution, the mode equals the median equals the mean? I would too. I would too. In a normal distribution, the mode equals the median equals the mean, for the reasons that we've gone through here. This is the most, at its highest, this represents when the curve is at its highest, it stands adjacent to the mode, which is here. Because the distribution is symmetrical, 50% of the scores are up here and 50% are down here. So this is also the median, and because the scores above the center of the distribution precisely counterbalance the scores below the center of the distribution, the mean is also here. So in a normal first of all, a normal distribution is bell-shaped, which means that it's symmetrical. It's symmetrical about the mean. That is, this score at the center of the distribution is mu, the population mean. First observation then about the normal distribution again is that it's bell-shaped, that is, it's symmetrical. More specifically, it's symmetrical around the mean. The second observation about normal distributions is that in a normal distribution, the mode equals the median equals the mean. Are there any questions about the general nature of the normal distribution? If not, let's forget momentarily the original units of measure. That is, we could be talking about dollars, we could be talking about scores on a personality test of some kind, we could be talking about height or weight measured in, on the one hand, feet, and on the other in pounds. If we, instead of measuring distance along the x-axis in those original units, we measure them in standard deviations, then we can simply track off, slice off certain portions of this curve. For example, we could go to a point that's -1 standard deviation, that is 1 standard deviation below the mean, -2 standard deviations, -3 standard deviations, and so forth. And up here we could go to +1, +2, and +3 standard deviations, and so on. Let me ask you this. What proportion of the area under this curve is between -1 standard deviation and +1 standard deviation? That is, this area in here.
Well, can't the total area only be 1?
The total area is 1 or 100%. So, with the acknowledgement, of course, that this curve never reaches the x-axis. It stretches on for infinity. Again, this is a hypothetical distribution. And all I'm trying to do now is make a transition away from the original units of measure and instead measure everything in standard deviations. Having done that, having standardized this normal distribution, we could then measure the distance along the x-axis in those units. That is, -1, +1, -2, +2 standard deviations, and so forth. And my question remains, if we do that, do we know what proportion of the entire area under the curve is between +1 and -1 standard deviations? Would you believe me if I just pulled out of the air 68.26%? You wouldn't believe that. Ye of little faith. You think I would lie to you? Let me put it another way. In a normal distribution, between +1 and -1 standard deviations contains 68.26% of all of the area under the curve. That is 68.26% of all scores in the distribution, in this normal distribution, stand between +1 standard deviation and -1 standard deviation. Most of us, on most things, are average. Between +2 and -2 standard deviations reside 95.44% of all scores in the distribution. And between + and -3 standard deviations, 99.72% of all scores in the normal distribution. If you are more than 3 standard deviations removed from the mean, you are a freak. In fact, if you're 3 standard deviations removed from the center of the distribution, you're a freak. Statistically, you're a freak. Because all that's left, you understand, outside of this region is 0.28% of all of the scores. Pardon?
For the third, if you're in the third deviation?
If you're outside of the range bounded by +3 standard deviations and -3 standard deviations, that is 3 standard deviations above and below the mean, all that remains, and I know where the confusion is coming, I think. That should actually point here. In this shaded area, these two shaded areas, there is they combine to provide 0.28% of all of the scores in the distribution. Let me give you a sort of let's jump ahead for a moment. And you don't have to put this in your notes, because this is in part why the normal distribution is critical to inferential statistics. In a court of law, in order to render a verdict of guilty, you're instructed, amongst other things, that in order to do that, you must be convinced beyond reasonable doubt that the defendant is in fact guilty of the crime. I have no idea in a court of law or in your head what constitutes reasonable doubt. But in data analysis, reasonable doubt means that your willingness to commit an error, your willingness to commit a specific type of error, the analog to finding an innocent person guilty, is at traditionally established at either 5% or at 1%. That means that if we now took a score, any score, and placed it in this distribution, we would conclude that it was critically dissimilar or significantly different from the center of the distribution, the mean, only if it resided approximately plus or minus, beyond plus or minus 2 standard deviations, because that includes a little over 95% of the scores. And in the case of, if we were only willing to take a 1% chance of being wrong, somewhere between 2 and 3 standard deviations. Would you agree? I'm not sure people are agreeing. I think they're just going, well, that sort of, yeah, let's go on. The whole basis, the whole purpose for testing for between group differences is to determine, in its simplest form, whether an observed real score differs from the mean of the scores, differs significantly. Well, in order to determine that that is in fact the case, that the observed score differs significantly from the mean, by tradition, that score must be approximately either 2 standard deviations removed from the mean, which is the case when you are willing to take a 5% chance of being wrong, because approximately 5% of the scores are of that kind. Or if you're willing to take simply a 1% chance of being wrong, then you have to extend further out. Let's try and see this in practice. But before we do, are there any questions about the normal curve or normal distribution?
Does this apply to curves that are more flattened out than this?
Regardless of the precise shape of the bell, the same relationships hold. That is, first of all, any normal distribution is symmetrical. It is symmetrical around the mean. Second, in any normal distribution, the mode equals the median equals the mean. And third, in any normal distribution, if you standardize that distribution, that is, if you measure the distance along the x-axis in standard deviation units rather than in the original units of measurement, be they dollars or SAT points or GPA points, 68.26% of the area under that normal curve, that is 68.26% of all of the scores in the distribution, are within the range plus 1 standard deviation, that is 1 standard deviation above the mean, and minus 1 standard deviation. That is 1 standard deviation below the mean. And further, 95.44% of all scores between plus and minus 2 standard deviations, 99.72% of all scores between plus and minus 3 standard deviations. Yes.
So relating this to reasonable doubt, if you were to have plus minus 3 standard deviation, that would be like 1%, which means that would be like the ideal scenario to like make accuse someone of being guilty. Like
let's approach it this way. What is the probability that any given score in this distribution will be between plus and minus 3 standard deviations from the mean? The probability is 99.72% or 0.9972, because 99.72% of the scores are within that range. So what is the probability that a score will be more than 3 standard deviations removed from the mean? 0.28% or 0.0028, because 0.28% of the scores are of that kind. The closer these scores are to the mean, you understand, that indicates that they share a number of attributes in common. They look very much like the mean. 68.26% of the scores look very much like the mean. If we were not tracking here scores having to do with GRE or SAT or anything else, let's imagine that what we're plotting here is physical attractiveness. You understand that if physical attractiveness in people is distributed normally, most of us are of average physical attractiveness. That's what it says. Very few of us are extremely attractive or extremely unattractive. That is, down here at the unattractive end, you have characters like the Elephant Man, Quasimodo, in terms of physical attractiveness, freaks. Up at this end, you have a small number of people. They all seem to live in Hollywood, and I hate every one of them. Up here, you have Denzel Washington. Up here, you have, I guess, Brad Pitt. I don't know. I'm taking a guess here. You know, I've strategically avoided using females as the example for very obvious reasons, and so I'm struggling a little bit down here. My point is here that there are out there. We don't know typically another person's GRE score. We typically don't know another person's SAT score or how much they earn a year. But by looking at people as they go by us, we do recognize levels of physical attractiveness. And let's assume that physical attractiveness in the population is distributed normally. All this does, it seems to me, is confirm, at some level, confirm your prior observations. There are very, very few very unattractive and very attractive people. Most people look pretty average. Second, what this distribution does now is to allow you to be more specific, because it allows you to talk in terms of proportion of scores, and those scores are typically attached to people. And so we could talk about proportion of people within specific ranges in this distribution. Most people are pretty average looking. Again, assuming that physical attractiveness is distributed normally, at least we would say 68.26% of the population is pretty average looking. And I got to say that confirms my observations. I will appeal to Seinfeld. 95% of people, undateable. Undateable. When he asked George, then how do they get together? George's response is alcohol. Enough of the frivolity. Let's get rid of these freaks. And let's get rid of this issue. Let's turn to z-scores or standardized scores. Z-scores or standardized scores. In order to standardize a score, you need to know three pieces of information. You need to know the individual score that you're seeking to standardize, that is xi. And let us presume that xi is 27. You need to know x bar or mu. Let me stick with the treating this as a population. You need to know mu. You need to know the mean of the distribution. And let's say the mean of the distribution is 30. Would you agree that we know already that this individual score is below the mean? That is, it's somewhere in the lower half of the normal distribution. The third piece of information that you need is the standard deviation of the scores. And let's say the standard deviation is 5. We can now transform this original score into its standardized or z-score. And the z-score associated with 27 in this distribution is given by the formula xi minus mu over sigma. That is the individual score minus the mean of the scores divided by the standard deviation of the scores. And you understand when you divide by the standard deviation, all you're doing is transforming the difference between xi and mu into units called standard deviations. So if we apply this formula, it's very straightforward. Xi is 27, mu is 30, and sigma is 5. So that the z-score associated with 27 is 27 minus 30, which is minus 3, divided by 5, which is minus 3/5, which is minus 0.6. Would you agree? Yes? Let's take another xi in the same distribution. This xi equals 41. We can standardize this score again this original score very easily by applying this formula. That is xi minus mu, 41 minus 30, divided by sigma, which is 5. So the standardized score associated, that is the z-score associated with 41, is 41 minus 30, which is 11, divided by 5, which is 2 1/5, which is plus 2.2. Would you agree? Are there any questions regarding how to compute z-scores? Because you'll be required to do this on the exam. You need 3 pieces of information, and then you need to apply the formula that combines those 3 pieces of information. You had a question. Could you press?
Are you going to give us xi?
You can only compute a z-score if you have all 3 pieces of information. So you must be given xi, you must be given the mean, and you must be given the standard deviation. And then you simply standardize the score, that is, compute the z-score, by applying this formula, which combines the 3 scores and indicates to you what you should do with those scores. Are there any other questions? Yes.
Will we have to be able to figure out the mean and then be able to compute the z-scores? Or are we going to be given all 3 of them
It's
together?
unlikely that you will be required to compute any of these scores. On the exam, you will certainly be required to compute mean, mode, and so forth, standard deviation, variance. But separate from that part of the exam, you will be required to compute some number of z-scores. And in those instances, you will be given each of the 3 requisite pieces of information. Okay? Are there any other questions?
Is a z-score, do we plot it? What do we do with it once we calculate it?
Aha. This is the who cares, so what? So now we know another trick, Douglas. You know, you told us about the normal curve, and we can now go out and bore our friends by telling them the same thing. And now you got us to compute z-scores, and I guess I could go home. The least you do with this is when you next see your parents, you say, give me a score. And they say 28. Give me the mean of those scores. Give me the standard deviation of those scores. And I tell you what, I can compute the z-score. I can standardize that original score. It'll please them. It will show them you're learning something, no matter how idiotic it is and how impractical it is. You don't do anything else with this stuff. That's as far as it goes. No, that's not true. That's not true. You do a lot of stuff with these scores, and we're about to get to that.
That was my question.
We're about to get to that. Now I've got to try, first of all, and do all of this again. Oh, my normal curve. I hate it. I hate it when it all disappears. Oh. Would you agree that at the center of this distribution is the raw score 30, which is the mean of the scores? That corresponds to a z-score of what? Let's do it. let's say that somebody scores that an individual xi is 30. We can transform this score of 30 into a z-score by applying the same formula. Xi is 30 minus the mean, which is 30, divided by the standard deviation, which is 5. Would you agree that's 0 over 5, which is 0? So that a score, the mean score in any standardized normal distribution is 0. Now let's take the first of these individual scores, xi. This person scored 0.6 standard deviations below the mean. Somewhere in here, would you agree? Minus 0.6. And the second person scored 2.2 standard deviations above the mean. Somewhere in here. Yes? Yeah? No? All I've done is take these standardized scores, and by standardized scores or z-scores, all we mean is scores measured in units called standard deviation. So we can now place them into a distribution that is measured in units called standard deviations. Individual 1 with an original score of 27, that score was 0.6 standard deviations below the mean, minus 0.6. Person 2 with an original score of 41 was 2.2 standard deviations above the mean. Yes? This is the easy part, because we're about to start going uphill. We're about to start going uphill. Because I'm going to ask you, what proportion of all scores were below 27? What proportion of people scored below 27? I'll take another sip on my vodka. I'm really not for it's not, it's water. How would you determine that?
Well, I mean, you can't determine it yet. You need to take your z-score. You need to. Yeah.
How would you determine that? Is anybody reading this book? If you're not, you're inviting problems. And that's, I'm stating no more than the obvious. I'm not berating you, I'm not threatening you, I'm just stating the obvious. If you're not reading the text, you're inviting problems. If you show up here expecting that I, in all my genius and brilliance, will explain things perfectly to you and you will walk out with perfect understanding, it ain't happening. The way this works effectively is if you read the materials before you show up, listen to me go over those materials and raise the questions you have about the materials. I know that you all went through this chapter and you've just forgotten momentarily that on page 98 there is a section called Using Table A. Well, let's go and see what Table A is like. This is all new to me too. It's just fun and games, isn't it? Table A. 6 columns of figures on 2 pages. 3, 4 pages. 4 pages, 6 columns of figures on each. Let's start with, let me ask you a second question and we'll start there. What proportion of all people scored above 41? Another way of, first of all, to answer that question, you understand, you first have to standardize the score, 41. And we've done that. That is, you need to transform it into standard units called standard deviations. And when we did that, we discovered that 41, an original score of 41 is 2.2 standard deviations above the mean. Assuming this distribution of scores is normal, my question now is, what proportion of all scores were above 41? That is, what proportion of all scores were above 2.2 standard deviations above the mean? How about we go to Table A? Table A actually has 3 components replicated over and over again. Column A says Z. That is the Z-score. In this instance, plus 2.2. So let's find the Z-score of 2.2. That score is on page 338 in the second set of 3 columns. Would you agree? Has everybody located a Z equal to 2.2? Has everybody with the text? Well, let's forget the pagination. If you find Appendix A at the back of whichever version of this text you're using, you should then easily locate 2.2. The second column in Table A says the area between mean and Z. The area between the mean and Z, here's the Z-score, here's the mean. The area between the mean and Z is this area. And it says 48.61. That is, in this instance, 48.61%. It would help if I were right-handed or had all of this stuff the other way around. Let me try and be more legible here. 48.61% of all scores are between plus 2.2 standard deviations and the mean, which is 0 standard deviations. Another way of expressing that is that 48.61% of the scores are between 41 and the mean, which is 30. The last column in Table A says area beyond Z. In this instance, that's this area here. And it says area beyond Z, 1.66. That is 1.66% of all of the scores in this distribution are, and in any normal distribution, are above plus 2.2 standard deviations. Pardon? Did I jump here?
Yeah, for 2.2.
Oh, this is. We're going to have to edit this mistake out because I never make mistakes. We're looking for a Z-score of plus 2.2, which is associated with an area beyond Z of 1.39. That is 1.39% of all of the scores in any normal distribution are above plus 2.2 standard deviations. In this particular context, we can say that 1.39% of all of the scores are above 41, which was the original score associated with a z-score of plus 2.2. So the answer to my question, what proportion of all scores were above 41, is 1.39%. Let me ask you this. We used a third score, a score of 30. And we discovered that it was associated with a z-score of 0. Let me ask you, what proportion of all scores in this distribution are above 30? 50%. 50%, because 0 standard deviation, a raw score of 30 is associated with a z-score of 0. That is, it's at the center of the distribution. If this is a normal distribution, 50% of the scores are above the mean and 50% of the scores are below the mean. So the answer to this question, what proportion of all scores in this distribution are above 30, and the answer to this question, what proportion of all scores in this distribution are below 30, is 50%. Let's move to what may be the more difficult case, and that is the question of what proportion of all scores in the distribution were below 27. 27 was associated with a z-score of minus 0.6. We agreed? So what we're looking for, would you agree, is this area in here. Yes? What we're looking for is the area beyond a z-score of minus 0.6. Yes? And we go through table A, and there are no negative scores. There are no negative z-scores. That's not a problem, because this distribution is normal, and so it's symmetrical. And so rather than use minus 0.6, we can use plus 0.6. Let's look at plus 0.6. A z-score of plus 0.60. Let's go to the area beyond z. The area beyond z is 27.43. That is not 27.43% of all of the scores in the distribution were below 27. Let me ask you, if we were to reach into this distribution randomly, what is the probability that we would select a score above 41? .0139 or 1.39%, because 1.39% of the scores are of that kind. If we were to reach randomly into this distribution, the likelihood of selecting a score above 30, the mean, would surely be 0.5. The likelihood of selecting a score below 27 would be 0.2743, because 27.43% of the scores are of that kind. Let me ask you a third question. What proportion of all of the scores are between 27 and 41? What proportion of all scores are in this now shaded area? How did you get 71.18?
I added up the area between 0.60 and the area between,
The area between, you added up the area between minus 0.6 and where? I'm not sure. I'm not sure. This is how you do it. It's a two-step, well, it's a three-step process. You've got to identify two numbers and then add them together. First of all, you need to know the area between minus 0.6 and the mean. So we go to plus 0.6 again, and we find that the percentage of scores between minus 0.6, that is 27, and the mean, that is 30, is 27.43. That is...
No, that's the beyond.
That's the area.
That's why I was confused. I was like, the area between the mean...
No, don't worry. It's 22.24. Yes? The area between the mean and z. Am I... God, let's do this again. Let's replay this again. It's a three-step process. You need to identify two scores and then add them together. The first score is the area between this z-score and the mean, and the second score that you need is the area between this z-score and the mean. The area between a z-score of 0.6 and the mean, I will make sure now, the area between the mean and z for a score of 0.6 is 22.57. So 22.57% of all of the scores in this distribution are between 27 and 30. You now need to know the proportion of all scores between the mean and the z-score associated with a score of 41, which is plus 2.2. So you go to a z-score of 2.2. And it says the area between the mean and z is 48.61%. That's supposed to be a 4. And now you add these two scores together. Is this what you did? There you go. So that's an 8. 71.18% of all of the scores are between, of all of these scores are between 27 and 41. That is between minus 0.6 standard deviations and plus 2.2 standard deviations. That's all you have to do with z-scores. Obviously, you have to locate the correct z-score in Table A. Otherwise, you're in a fix. First of all, the nature of the normal distribution. Let me just go through this and I'll get to your question. First of all, the nature of the normal distribution. It's symmetrical. Specifically, it's symmetrical around the mean. Secondly, the mean, the mode, and the median are equal. Third, if you measure the distance along the x-axis in units called standard deviations, you can specify in any normal distribution the proportion of all scores that are between plus and minus 1 standard deviation, plus and minus 2 standard deviations, plus and minus 3 standard deviations. In fact, if you use Table A, you can specify the proportion of all scores anywhere in the distribution. The other major topic this morning is obviously standardized or z-scores. In order to transform original scores into z-scores, you need 3 pieces of information. The individual score you're seeking to transform, the mean of all the scores, and the standard deviation of all of the scores. And you then compute Z by subtracting the mean from the individual score and dividing that difference by the standard deviation. And clearly we could do that very simple arithmetic process for an infinite number of scores. And you can then place those standardized z-scores into the standardized normal distribution. The other trick that we learned was determining the proportion of scores above a particular score, the proportion of all scores below a specific score, and the proportion of all scores between any two other scores. And to do that, you simply use Table A. Understanding that while there are no negative z-scores included in Table A, you simply use a positive z-score of that value because the normal curve is symmetrical. Any statement that you make about one end of the distribution, you can make about the other end of the distribution. You had a question.
If we're going to have to calculate the portion of the test, will we be provided table?
The question is, if you're going to have to compute proportions or areas between one score and another, or above one score or below a score, will you be provided Table A? The answer is yes. You will be allowed to bring with you a Xerox copy of Table A. And if you show up and you say, I don't have a Xerox copy of Table A, you are out of luck. Are there any other questions? Hearing none, I declare this meeting adjourned. Let me